Hi everyone, this is Dr. Swaminathan SM. Now I am going to discuss about the topic called Applications of Rootlocus Diagram and the Nyquist Stability Criterion Condition Introduction. So first thing, what are the applications of Rootlocus diagram? So we can find the stability of the system using root locus. And next, effect of the variation of parameters. So we can find the limits of these parameters to determine the stable operation. So for our convenient, we can make the design stage of the system based on this some latitude in the choice of the system parameters. So we can change the system parameters, that is like stability and loop gain and system gain. Everything is based on the root locus diagram. And the root locus techniques that can be determine the dynamic response of the system, and this method also associated with the transient response of the system, particularly investigation of the stability of the characteristics of the system, and also to determine the stability boundaries of the system based on the suitable parameters given to the root locus analysis. And next, it governs the transient behavior. Transient means that is nothing but based on the time the output will be varied. In root locus technique, the graphical procedures that defines in the S plane of the system. And again, the complex plane that plays when we are drawing this root locus diagram, that's maybe real or complex. So a open loop transfer function used to simplify the procedures, and also the plots that is drawn using information of the closed loop system to illustrate the variations of the parameters to find the system stability and the nature of the system, that is response. And next, the branch of the root locus, it shows all possible values of one root when parameter is varied. All the separate branches of the root locus plot give the effect of the variations of the parameters. And next, the root locus plot technique is essentially for the time domain technique. And next, the frequency response data that may be varied in the root locus plot. By using this technique, the open loop poles and zeros that can be modified and satisfy the requirements that may be closed loop poles and zeros. So it may be not maybe noted that the slight change in the pole zero configuration may cause a significant changes in the root locus configuration. And next, the Nyquist stability criterion that determines the stability of the closed loop transfer function, closed loop system, and from its open loop transfer, that is open loop frequency response and open loop poles. So mathematically, you make this contour, that is S is equal to x plus jy, and just substitute f of s, that mapping. So mapping the contour A through the function f of s to contour B. So S plane, that is sigma, and j omega, that is q is nothing but the contour A, and again contour B is given. So q is given to the q dash in the f plane. So real axis and the imaginary axis. So based on the contour plane, you can compare that the S plane into F plane using through the f of s equal to s, that is s minus z1, that is the zeros condition. So again contour A to contour B. Again the contour A to contour B, that is the poles. So f of s equal to 1 minus s minus p1. So p1 is nothing but poles. So these are all the reversely proportional. So look at this contour B, and again the contour B in the downside. So these are all the important things we need to consider this part. And also we can get the R is equal to 1 by V, that is the Nyquist stability criterion condition. And again the contour B that maps the counterclockwise direction. If f of s has just the poles and it's encircled the contour, also you should verify if the pole zeros f of s, that is enclosed by the contour A, that is mapping in the encircles plane. And again the Cauchy's principle of argument, f of s is analytic function of the closed region of the complex plane in the given figure, except at a finite number of points, that is namely poles of f of s. So n is equal to z minus p, that is the condition. So where z and p stands for the number of zeros and number of poles, that included their multiplicities of the function, that is f of s inside the contour. And again, the argument of f of s equal to z minus p into 2 pi, that is nothing but n. So n is equal to z minus p. So it satisfies the terminology called the principle of argument, that is the Cauchy principle arguments. So Nyquist plot, you can see the poles of the polar plot of the transfer function d of s, that is equal to 1 plus g of s into h of s, the contour s plane. From the contour, it covers the whole unstable half of the complex plane, that is r tends to infinite, since the d of s is the function. So according to the Cauchy's principle of argument, that must be analytic at every point on the contour. So the poles d of s in the imaginary axis, it's encircled in the infinity small circles. So the Nyquist criterion condition that satisfies these conditions. So z is equal to p plus n. Z is nothing but zeros, p is nothing but the poles, and n is nothing but the encirclements, number of encirclements, that is minus 1 comma j0. So this is the Nyquist stability criterion conditions. Thank you.